I am wholly dissatisfied with this proof, okay? Because this proof, the entire thing is predicated on the fact that you knew what the answer was before you started, right? If we didn't know that, you got nowhere to go, right? Like you're back here where you started. If this was the only thing written on the page, you're like, where on earth does this guy come from? And the answer is, it comes by someone else knew the answer, okay? Now, I will say, there's still value in that. When we look at mathematical induction, the whole principle of mathematical induction works on the fact that you know what you're going to get before you start, okay? But there are things about mathematical induction that make that still an amazing sort of technique, even if you do know what you're supposed to end up with. And also, secondly, we can integrate that. We can integrate this. We have the tools we need. Like someone did this once upon a time, worked out that to get from this, you'll end up with that, and they didn't know what it was before they started, and they didn't just like blindly start differentiating things until, oh cool, I got it. They actually did this analytically. So here comes method 2. Hold on to your hats. It's not easy. That is why, rather than the question walking you through with multiple parts and saying, okay, try this, they've just gone straight to this because it's so much quicker and so much easier. But when we do this method, do it from scratch, as it were, like so. It's going to be, I think we're going to learn some stuff. Okay? So let's have a go with this. Now, when you look at this on the face of it, especially given the context that we've been looking over this week, what's the first thing that jumps out for you as a strategy you could try to make this easier to work with?
Sub in a tan theta.
Yeah, so I want a substitution, a trig substitution of some kind. Because I've got a sum of squares down here, not a difference, sine and cos are not going to be useful to me. I want tan and sec, right? That's what's going to give me the relationship. So I'm going to say, let x equal a tan theta, right? If x equals a tan theta, I'm going to need to have the derivative with respect to theta so I can change the variable of integration, which of course is, what is the derivative? Great. Okay, but actually I don't even want that. I want to have dx on the denominator, so I'm going to write 1 equals a sec squared d theta dx. You happy with that? Okay. So now I think I'm pretty much ready. I mean, it's indefinite. Okay, so I'm going to go and try my substitution. This is equal to the integral of, I'm going to substitute my my 1 up the top with that guy, so I can change everything. A sec squared theta dx. On my denominator, you can see I've got a squared plus what? A squared tan squared, yeah? That's good. And there's my dx, which promptly cancels as soon as I've written it down. Okay, so far so good. You can see I can do some pretty impressive cancelling here, right? What am I going to get? I've got my a sec squared on the numerator. Down here, what can I do? I can do two things, right? I can take out the square root of a squared, which of course is just a. And then this is 1 plus tan squared that gets left behind. Okay, so it's the square root of sec squared. Okay, so you can see a's cancel. That's good. So now what do I do with this? Because we know we can't just simply turn this into the one of the cases. There's what am I going to deal with this absolute value? Yeah.
You have to say that 1 over a squared plus x squared is always modulo 0.
Okay, so I need to come back to the restrictions that were in place. Okay, so when you have a look at this, I want, what do I want? I want x squared. I want the restriction on that to be, well, what restriction do I want?
Greater than
X.
Look at it carefully. What restriction exists on x here?
there is no
There isn't one. There isn't one. Okay. So therefore, when I have a look at this, I need to be able to deal with all my values. But that's okay because have a look at what we used for our substitution. Do you remember when we did this before? This guy, if you go between, say for instance, I mean it's positive values, so I could go from 0 to pi on 2. But because of this guy, you know what? I'm just going to go all the way. I'm just going to go theta pi on 2. Right? You want any value of x you like, that's okay. Tan will get it for you, right? Because tan just goes all the way, he gets any value you want. And the reason why I do this is because what is sec? Right? Sec is 1 over cos, 1 over cos. This is what cos looks like between minus pi on 2 and pi on 2. So therefore, its reciprocal is going to look like this. It never gets there, right? It goes through there. It's got its asymptotes. So therefore, within this domain, this guy, always positive, right? Does that make sense? So therefore, I'm going to say this is sec squared theta on sec theta, and the reason is because of this guy. Okay? So it was a bit scary at first when we were like, wait, no restrictions? I need some restrictions. But when you think back to what these are, it's like, yeah, I can restrict and I still get all the values that I want. So this can be restricted even when this is not. That's kind of cool. Okay? So that's why I've got the positive case. Cancel, cancel. So I'm left with this. Okay. Now, this seems like progress. It is progress. But it's problematic progress, right? Because what do you do with this? This is not a standard form, right? What could we do? Yeah.
You multiply top and bottom by sec theta plus tan theta.
Okay. Now, again, what I can do is if I know it, I can see there's actually some reverse chain rule that I could use here that's going to get me to my log. But you can only do that if you know it, right? If you know it. And so even though, again, that's a part and it will be quicker, it'll get this out in 3 or 4 lines. I don't want to go in that direction because again, it's assuming a lot. It's assuming I already know what the integral of this basically is, which I think from memory is log of sec theta plus tan theta. Okay, so therefore, how are we going to get this? Okay, what have we learned over the past little while for dealing with integrals that are? This is a rational function, isn't it? It's actually 1 over cos. What could you do with this thing? What techniques do you have? 1 plus tan squared. Okay, so you want to try and use some form of the Pythagorean identity? Yeah? It could work, okay? Except I don't have, like, I mean, that's going to send me back to this, right? Like, do you see that's the square root of sec squared? That's that thing. That's where we actually came from. So I'm not gonna use that, and the reason why I know not to go back in that direction is because I just used it. So it's a little bit like substituting in simultaneous equations, substituting the equation back into itself. So it's like, oh, cool. 1 equals 1, yay for me, okay? So I can't reuse it.